Hello everyone. Welcome back to PyLadiesCon 2024. I'm delighted to introduce our next speaker, Emily Shen. Emily is a scikit-learn enthusiast and an open source contributor and a strong advocate for diversity and inclusion in STEM. Today, Emily will speak about the adoption of the Array API standard in scikit-learn. Let's give a big welcome to Emily.
Hi, everyone. Thank you so much for coming to my talk. I am super excited to share the next 20 minutes with you guys to talk about scikit-learn and Array API. Let's get started. So, my talk is called The Adoption of the Array API Standard in scikit-learn and How to Use It. Before we get any further, let me tell you who is talking to you. So, hi, everyone. My name is Emily, and I am a open source scikit-learn contributor, and I was also an intern at Probable, which is the official operating brand of scikit-learn. In the next 20 minutes, I'll cover 4 things. So first, what is scikit-learn? Second, what is Array API? Third, why is scikit-learn adopting Array API? And 4 is a short, quick demo that summarizes the previous 3 topics I talked about. First up, what is scikit-learn? So scikit-learn has this logo on the bottom right corner. It's also on my shirt. It is a open source Python library for machine learning. It is widely used in data science, especially in academia and research for data mining, analysis, and predictive modeling. Scikit-learn focuses on shallow networks as opposed to deep neural networks that a lot of people are familiar with these days, and it's quite popular. And therefore, scikit-learn is good at classical machine learning algorithms such as classification, regression, and clustering. So that was a very brief overview of what scikit-learn is. Let's talk about what is Array API. Array API is a specification that standardizes the core functions and behaviors of array libraries in Python to improve interoperability. That was a mouthful, so let me explain a little bit more and break that down for you. So Python is open source, and it has a lot of libraries that are also open source that you could use in Python. And these libraries contain many functions that you and I and any developer don't have to write out themselves from scratch, which is awesome. But because it's so open source, it poses one problem. Many of these libraries contain similar functions like sum and mean, and they all output the correct answer, but the way to use them is slightly different. For example, some may expect the inputs to be in a particular type, and some may output in an integer format, in a double format, in a different namespace than a different library. So because their behavior slightly differs, it's very difficult to use multiple libraries in a project without making adjustments in between. And figuring out those problems requires either reading a lot of documentation or reading a lot of error messages, and it's not very efficient. So Array API standard is trying to address that problem by ensuring common functions like sum and mean, and a lot of other ones, work the same way across different libraries. So not only does it make it easier for developers to use different libraries in their projects, it also means more stability in their output as well. So you input something, the output will be exactly the same type, the same precision, everything. So now that we talked about what scikit-learn is and what Array API is, how is Array API beneficial specifically in scikit-learn's use case? The vast majority of scikit-learn algorithms are written in NumPy, which is a CPU native library. However, with Array API, these CPU native algorithms can run on GPUs with PyTorch and CubePy. So how that works is when you run an algorithm, and it will look at what type of input you're using. If it's a NumPy input, like a NumPy array, for example, it will run on CPU because NumPy is CPU native. However, if you input it into like a torch array or a CuPy array, then the array API adopted function will look at the input type and understand that it is a torch array, for example, and it will run on GPU. And as many of you probably already know, GPU runs a lot faster than CPU, which means it will increase performance by a lot. But that's not the only benefit of adopting Array API. There's this thing called just-in-time compilers, which compiles code while the program is running, as opposed to compiling everything before runtime, then goes into runtime. So this means that performance will increase as well because you're not taking the extra time to compile everything. This sounds amazing. However, JIT compilers have very strict expectations on what a function's input, output, and behavior are. Luckily, JIT compilers' expectations align exactly with Array API standard, which means if we adopt Array API, we could also use JIT compilers as well. Similar story to JIT compilers. Using Dask Array, we're able to do out-of-core or distributed computing. That just means you can break down a very large task into smaller tasks, and these smaller tasks can be processed in parallel across different GPUs. However, similar to JIT, Dask arrays also have very strict expectations on what a function's input, output, behavior should be. And these expectations align also with the Array API standard. At this current point, though, we're not really worried about JIT compilers or Dask arrays just yet. We're just trying to make NumPy work. And we're seeing good progress, which I'll be showing very shortly in this demo. Before I go into the actual demo, though, I must acknowledge that the code I'm about to show, I got it from Olivier Grizel, who was my mentor and still is my mentor when I was an intern at Probable. This is my demo on the Colab. Because we're limited for time, I already installed and ran a bunch of things, but I will just briefly go over what they mean. So NVIDIA's SMI just ensures that you have a GPU installed and enabled and configured correctly. I'm just cloning into my main branch of my scikit-learn repo right now. This is the equivalent of installing scikit-learn on your local machine. These are just some dependencies that you would run after installing scikit-learn so that you can enable its full functions. This just makes sure that I actually have CuPy installed, and CuPy is what we'll be using today to demonstrate GPU functions. In order to use Array API, you have to install this Array API compat thing. And Array API compat basically it just contains a bunch of functions that's already written for you in Array API compatible format. And here, it just confirms that I've installed scikit-learn correctly. One thing to point out, though, is that the version of scikit-learn I'm using is an unstable version because I am a developer on it. So the dev 0 indicates that it's an unstable version. But 1.6 is due to release very, very soon. So this dev will be removed. And for those of you who are interested, you're able to install the same version I'm using right now very, very soon. And it will be stable. Another catch with the Array API library is that you need to have SciPy to be version 1.14.0 or above because SciPy is also working towards Array API standard compatibility, and SciPy is one of our dependencies. This is the code I actually meant to demo. Here are the necessary imports, which I will be diving into later. As I just mentioned, SciPy is also working for Array API, and their way of enabling Array API is to set the OS environment to 1. This line is scikit-learn's way of enabling Array API, because as of right now, you have the choice of using Array API or not. And if you opt to use it, you have to tell scikit-learn that you want to use it. And this is the way to tell it. Here, I'm just writing two very large numbers, which will later correspond to the number of samples I want. and how many features each sample has. In this demo's case, I have 250,000 samples, and each sample has 1,000 features each. The solver I'm using today will be Ridge with SVD. For those of you that are not familiar with resolvers or regressors, you can just imagine this as a math formula or some sort of rule that separates your data so that it could maximize difference without overfitting. But essentially, it's just a math formula that you want to fit across your entire data set. Here, I'm just printing out the shape, which will correspond to 250,000 by 1,000. And I'm generating random samples because I don't actually have any real samples or data set that big. I'm just generating random samples using CUDA. I am saving it in this matrix called W, and then I'm generating targets that correspond to those random samples using a multiplication plus some random noise. But basically, you can just imagine X CUDA and Y CUDA being your sample and target. Well, data and target. So these are in the CUDA namespace, which, if you recall from what I said earlier, is compatible to run on GPU. Here, I'm converting them to NumPy arrays, which are typical input types to non-array API NumPy CPU native functions. And here I'm just printing the data size in megabytes to show you how big that sample is. Earlier, we imported perf counter. Perf counter is what I think of as a timestamp. So tick is the start of the timestamp before we run a very demanding function, and talk is the timestamp after the function has been ran. And we subtract tick from talk, so here, to see how long this function took. So I basically, in the last two blocks, I run ridge.fit twice, except one, I input the CUDA type, and the other, I input the NumPy type. And we'll be able to see how long each of these took to prove that GPU acceleration indeed is better, and it will happen with Array API enabled for scikit-learn. Let's run this. So like I mentioned before, you could see the data is 250,000 by 1,000, and the data size is 1,000 megabytes, which is 1 whole gigabyte, which is a lot. We could see that this GPU process fit has already finished, and it took 1.47 seconds. And now if you see this little green triangle here, it is working very hard to do the CPU fit on Ridge. While we wait, let's talk about what this line means. This line corresponds to this line. So basically, Ridge CUDA coif has 1,000 data points. So it's like an array of the size 1,000, and it corresponds to the end features, which is also 1,000. Oh, look, it ran. Anyways, these coefficients just means how much each of these feature weighs in the training process that will give you the best result. Now that NumPy has finished running, we see that the NumPy fit took 81.74 seconds versus the PyTorch GPU fit took 1.47 seconds. So you could see that the GPU acceleration indeed does happen with Array API enabled in scikit-learn, and it will vastly improve your performance when you're fitting something on your dataset. So that is the end of my demo. But one more thing I would like to show you before going back to my slides is that we have this mega issue in the scikit-learn GitHub repo. We have this very long list of functions and tools in scikit-learn that we're working very hard to make it Array API compatible so that you can have GPU acceleration on more tools in scikit-learn. Let's just keep scrolling to see how long this list lasts. It's a lot. That is actually the end of everything I have to talk about. So thank you for spending the time with me. If you have any questions or would just like to chat, I'm available over email as well as LinkedIn and X or Twitter. Feel free to reach out. I would love to chat and let me know what you think as well. Before I end this talk, though, I have input 2 links on the bottom of my slides here. The first one is the official Array API page on what's getting adopted in their standard, if you're interested in reading more about it, as well as the second link here is the scikit-learn official website, if you're interested in using or becoming a contributor. Thank you so much for coming to my talk. I hope you enjoyed it and you learned something. Thank you again.
Thank you so much, Emily. It was a great talk. I hope so everyone enjoyed the talk. It was really good. Thank you so much for giving us your time for this conference. And just let's continue with the conference.